Welcome back, everyone, to Flight Vehicle Dynamics. This is lecture 3 in week number 2. So last time we saw that given two reference frames with the same origin, so for example, A with origin in O and with the three versors A1, A2, and 3, and the reference frame B with the same origin O, but with three different versors, B1, B2, and B3, we can express a vector v in terms of coordinates of reference frame A or coordinates of reference frame B. And in order to go from one set of coordinates to another, the matrix that we use to go from one reference frame to another is called the direction cosine matrix, which is also known as a rotation matrix or a change of coordinates matrix. In fact, you can think about this whole process as either a change of coordinates between B and A or a rotation from B to A. So by applying this mapping, this rotation given by this matrix, you can think about taking the versors of reference frame B and align them with the versors of reference frame A. So that is the concept of rotation matrix. Or if you want to think about it as a change of coordinates, well, then you have a vector expressed in the coordinates with respect to reference frame B, and by applying this transformation given by this matrix, you get the very same vectors, but with different coordinates, and those refer to reference frame A. So the two things are actually equivalent. It's just a different perspective, but nevertheless, the rotation matrix or the direction cosine matrix or the change of coordinates matrix is the same matrix. We also saw that the way RAB is constructed is by taking the 9 inner products between the versors of A and B. So if you recall, we have RAB is given by A1 inner product B1, then A1 inner product B2, and so on and so forth. And so we have to complete the 9 entries of this matrix with the 9 different inner products between the versors. Now, this is not a very convenient way of constructing the rotation matrix from B to A, because, well, first of all, there are 9 inner products. It's not the most convenient way. It is a possible way, but it's not the most convenient way. The way that we will construct this rotation matrix between one reference frame to another is actually by applying 3 independent canonical rotations, which are also known as elementary rotations. But before proceeding, I want you to realize that every time we write RAB, we kind of have to read it from right to left, in a sense that this rotation matrix goes from B to A. So we have to read it in this direction. So this is the rotation matrix that from B will align B to A, or given a vector expressed in the B coordinates will give us the coordinates of the same vector in the A reference frame. Okay, so moving on with the 3 types of elementary rotation. So let's analyze one rotation at a time. And these rotations are about one axis at the time. So let's consider the first one. So of course, A and B, they share the same origin, and they also share um, the z-axis. Well, in the beginning, they share everything, but the rotation is performed about the common z-axis. So you can see here in to the left, we have a three-dimensional visualization of the two reference frames. And you see that we rotate about the z-axis so that uh, the x and the y-axis rotate about an angle of theta. So now there's an angular separation between the old axis xa with the new axis xb, and from the old axis ya to the new axis yb, and the angular separation is in both cases equal to theta. So now if we take a look at the same picture, but we focus on the x and y plane, so it's just as if we were looking at things from above. So we're just concentrating on what happens in the xy plane, then it's easier to see the rotation. So once again, we have xa rotates into xb and ya rotates into yb. And here in the orange and blue, I drew the versors of the reference frames. So we have A1 and A2, and B1 and B2. So now what we want to do is let's take the three versors that characterize reference frame B, and let's write them down in terms of B coordinates. And then we're going to try to do the same in terms of A coordinates. So B1 expressed in the reference frame B is simply 1, 0, 0. That's trivial. And so is B2 in the reference frame B, it's 0, 1, 0. And B3 in the reference frame B is 0, 0, 1. Now, from the picture, let's try to see what the coordinates are of the very same vector, so B1, but now expressed in the A reference frame coordinates. So let's take a look at what happens. If we project B1 into XA and YA axis, we see that the component in the XA direction of B1 is simply cosine of theta. Now let's do the same thing in the YA direction. So the component of B1 in the YA direction is sine of theta. And of course, the component of B1 in the Z direction is 0 because B1 lies completely in the XY plane. Whether it is XA, YA or XB, YB, the plane is the same. Now let's take a look at the vector B2, or well, I should say the unit vector B2 or the versor B2. Now, if we, from the drawing, we look for the coordinates in the A reference frame of such versor, we see that in the XA direction, we have a negative component, which is equal to minus sine of theta. And then the projection of B2 in the YA direction, so this part over here, is equal to cosine of theta. And once again, the Z component is 0. Now, what about B3? Well, B3 hasn't changed. B3 is the same in the A and in the B reference frame. We take a look at here. So its components are going to be the same in the A and in the B reference frame. So it will remain unchanged and equal to 0, 0, 1. Okay, so now how can we use this information in order to construct our rotation matrix? Well, we know that we have that a vector expressed in the reference frame A is equal to RAB times the same vector expressed in the reference frame B. So now if we consider as our vector V, our vector B1, well, we have B1 expressed in both the A coordinates and in the B coordinates. So we know that B1 expressed in the A coordinates is equal to RAB times B1 expressed in the B coordinates. So we have B1A, which is cosine of theta, sine of theta is 0. And then we have our rotation matrix whose entries we don't know. So I'm just gonna call them R11, R12, R13, and so on and so forth. And then we have the vector B1 expressed in the B reference frame, which is simply 1, 0, 0. So notice that if we multiply this matrix whose entries we don't know with the 1, 0, 0 vector, we're pretty much only retaining the first column of such matrix. So the result is R11, R12, and R13. Well, so we know now that R11 is equal to cosine of theta, R12 is equal to sine of theta, and R13 is equal to 0. So by looking at what happens to versor B1, we found the first column of the rotation matrix RAB. Very good. So now let's repeat the same thing for versor B2. So we have that B2 expressed in the A coordinates is equal to RAB times B2 expressed in the B coordinates. We know B2A, we know B2B, and so let's see if we can get some other piece of information about RAB. So B2 expressed in the A coordinates is what we saw over here, is minus sine of theta, cosine of theta, and 0, which is in turn equal to our rotation matrix times B2 expressed in the B coordinates, which is simply 0, 1, 0. And so now, as we did for B1, for B2, we're going to get the second column of RAB. And finally, for B3, well, that is even easier because B3 in both A and B coordinates is equal to 0, 0, 1. So 0, 0, 1 is also going to be the third column of our rotation matrix RAB. So now we found all the elements of RAB. We found column-wise. So we can fill the matrix, and of course, we can have the rotation matrix from B to A, although once again, it is written RAB, but that means rotation matrix from B to A. If you remember earlier, well, maybe I didn't make it as clear, but I want to make it clear now. We think that we are starting from reference frame A, and by applying this rotation about the z-axis, we get to reference frame B. So what we're really looking for is the rotation matrix from A to B. So given our notation, that would be RBA, because this rotation matrix, reading it from right to left, tells us that we're going from reference frame A to reference frame B, and this is what we want. But remember that if we have RAB, getting RBA is very easy. In fact, RBA is simply equal to RAB transpose. So that's how we got this matrix over here. And since it is a rotation matrix about the third axis or the z-axis, and how much is this rotation? Well, it's angle of theta. Then we're going to use also this notation here. So we're going to call it R3. So 3 refers to the axis number. And the argument is simply the amount, the angle that we rotated. So our rotation matrix RBA is also called R3 of theta. And you can simply compute the determinant of R3 theta, and you see that that is equal to 1 as expected. That is one of the properties of rotation matrices. Their determinant is always equal to +1. Now we can repeat the same analysis, but now starting from the reference frame A, we get to the reference frame B by applying a rotation about the y-axis. So in the end, we're going to have that the y-axis in both A and B reference frame remains unchanged. What changes is the x-axis and the z-axis. So as we saw before, if we take a look at just the plane in which the rotation takes place, now this plane is the xz plane. And as I did before, I can write down the versors and their components in both A coordinates and B coordinates. So I don't think I have to repeat the same thing, but the key thing is that you express once again the versors of B in both the B coordinates and in the A coordinates. And the way you do that, you just check visually. And as it was for before, now we have that B1, B2, and B3 in the A reference frame represent the columns of the rotation matrix AB. So we find that RAB for an elementary rotation about the y-axis of an angle theta is equal to cosine theta 0, sine theta, I'm reading row-wise, 0, 1, 0, and minus theta, minus sine of theta, 0, and cosine of theta. Of course, once again, since we're starting from A and we're going to B, then we're really interested in the rotation matrix RBA, which is the transpose of RAB. And so we're going to name this RBA as R2 theta. Of course, 2 now is because we are applying the rotation about the y-axis. And also in this case, we can check the determinant and see that it is equal to 1. Well, now guess what? We're coming to our third elementary rotation, and the axis that is and now about which the rotation is performed is the axis X. So it's really the same thing about a different axis. Now, The two-dimensional plane is going to be the YZ plane. That's the plane on which the rotation actually occurs. And so we can find the rotation matrix R1 of theta, and that is 1, 0, 0, 0 cosine theta sine of theta, 0 minus sine of theta cosine of theta. So here I'm not spending, I don't want to waste time repeating the same steps, but I advise you to go through them and try to reconstruct everything that I wrote. And of course, if you had doubts, please contact me. And don't be afraid. Just send me an email. And even if you think it's a dumb question, it's better to ask it earlier than later, because I don't want you to have doubts and then maybe be confused right before the midterm or any of the exams. Okay, so even in this case, the determinant is checked to be equal to +1, so we're good to go. So these are the three elementary rotations that we're going to use in order to construct a more general rotation between two reference frames A and B. So in these three elementary cases, the rotation was just a simple rotation about one axis at the time. But what if we have a more complex rotation? Well, we can get to this more general rotation by applying three independent elementary rotations. And by independent, I mean that two successive rotations cannot be about the same axis. In fact, if I were to apply a rotation, let's say I start with a rotation of 20 degrees about the x-axis, and then the next rotation is about of 10 degrees about, once again, the x-axis. Well, it wouldn't be an independent set of two rotations, because it's like having one rotation about the x-axis of 10 plus 20 equals 30 degrees. So every time that you apply rotation, you have to change the axis about which you are rotating. But before going there, I just want to write down a general form for the rotation matrix between A and B. So either if we go from B to A, or if we go from A to B, so RAB or RBA, I want to give you guys general expressions on how to form such rotation matrices. So if you have the expression of the versors of B, so B1, B2, and B3 expressed in the A reference frame, then if you put them column-wise, well, you get RAB. And if you place them row-wise, so B1 A transpose, B2 A transpose, and B3 A transpose, you're going to get RBA. What if you had the versors of A1? Well, the versors of A, so A1, A2, and A3, expressed in the B coordinates, well, if you take them row-wise, then you get RAB, and if you place them column-wise, you get RBA. Of course, you get from here to here by applying the transpose, and also right here. Otherwise, the more general form would be to compute the 9 inner products, as I reminded you earlier. A1 inner product B1, so on and so forth, all the way to A3 inner product B3. And if you want to have RBA, well, then you take first the versors of B and then multiply, in a sense, of dot product or inner product with the versors of the reference frame A. So here I'm just writing down that B1A, B2A, and B3A represent the versors of the reference frame B in the coordinates of the A reference frame, whereas A1B, A2B, and A3B represent the versors of A reference frame in the B reference frame coordinates. The only thing that I didn't write down is the fact that B1, B2, and B3 in the B reference frame are simply 100, 010, and 001. And also A1, A2, and A3 in the A coordinates are also 100, 010, and 001. But that doesn't give us any useful information. All right, so going back to our elementary rotation, I can summarize the three elementary rotations about the z-axis, the y-axis, and the x-axis. And here I'm shortening the notation by using c theta for cosine of theta and s theta for sine of theta. So now we can use, as I said before, these elementary rotations to form more complex coordinate transformation. And the first natural step would be to combine two elementary rotation. So we're going to have a composition of two, and I want to stress again, independent elementary rotations. So independent means that they're not going to be about the same axis, or they cannot be successive rotations about the same axis. They're not independent. All right, so the logical structure that we're following is the fact that we are starting from a reference frame A, then we're moving to a reference frame A prime, and then we're arriving by performing a second rotation to reference frame A double prime. So each of these three reference frames, they share the same origin, I would say, which is O, but they are characterized by different sets of versors. So the reference frame A will have A1, A2, and A3. The reference frame A prime will have A1 prime, A2 prime, and A3 prime. And finally, A double prime will have versors A1 double prime, A2 double prime, and A3 double prime. So you see that by performing two rotations, we are switching about three different reference frame. Okay, well, that makes sense. I think I don't really have to explain that. So now if we have a vector v expressed in the A double prime reference frame, that can be written as the rotation matrix between A prime and A double prime times the same vector expressed in the coordinates of A prime. Now, what is VA prime? Well, VA prime is the rotation matrix between A and A prime times the same vector expressed in the coordinates of reference frame A. So now if we substitute this expression over here and we put it in the first equation, we're going to find that VA double prime is equal to R A double prime A prime times R A prime A times V A. So finally, we have the vector expressed in the coordinates of our reference frame A double prime is equal to, well, the vector in the A coordinates pre-multiplied by the rotation matrix that takes us directly from A to A double prime. But you see that this rotation matrix is nothing but the multiplication of two elementary rotations. So R A double prime A is equal to R A double prime A prime times R A prime A. So here, once again, I'm telling you that in order for them to be independent rotations, so R A double prime A prime and R A prime A, they have to be about different axes. They cannot be about the same axis one after the other. So now we have a bunch of different choices because each of these two rotations, so the first rotation and the second rotation, can be about axes 1, 2, and 3. So we have a bunch of different choices that will give us our final rotation matrix from A to A double prime. And let me repeat myself once again. Why is this the first rotation and why is this the second rotation? Because we're reading things from right to left. So logically speaking, we are starting from a vector in the A reference frame, then we are applying a rotation from A to A prime, and then we are applying another rotation from A prime to A double prime, and then finally this gives us V in the A double prime coordinates. So the way you want to read these expressions are from right to left. You start from the very right, V in the A coordinates. We change from A to A prime with the first rotation, then we apply a second rotation from A prime to A double prime. And this whole thing gives us the coordinates of the vector in the A double prime reference frame. All right, so here I summarize in a table all the possible combinations of these two rotations. So here I'm indicating the first rotation, and of course, here I'm assuming that we are rotating about two different angles when it comes to the first and the second rotation. They don't necessarily have to be rotations of the same quantity in terms of angle. So I'm going to call the first rotation or the angle psi. And so we have three different choices, R1, R2, and R3. And then when it comes to the second rotation, well, the second rotation, I'm going to keep the angle theta. And we also have three choices, R1, R2, and R3. So let's see the overall combination between these two rotations. So R1 and R1 is not possible because it wouldn't be a succession or a sequence of independent elementary rotation because you would have two rotations about the same axis. So you would just have R1 of psi plus theta. So that wouldn't, that is not an option. Well, now if we take this case, for example, we have R1 times R2. So first rotation goes to the right and then second rotation to the left. And you see that we can complete the whole table. And so we have three cases in which the rotations are not independent, and the remaining six cases give us different, unique sequence of rotations that will take us from reference frame A to reference frame A double prime. So we have six choices. And in the table, I've dropped theta and psi as an argument just to avoid making things too cluttered. Can remove this. All right, so let's take, for example, the rotation R2 theta times R3 psi. And here I'm repeating for the millionth time that the first rotation is the one to the right. So we really start from R3 of psi, and then we apply the rotation about the y-axis of an angle theta. But then mathematically speaking, we have to go from left to right. So when we are actually multiplying the two rotation matrices, then we have to multiply them in the correct order. So it is indeed R2 times R3. So in this case, if we multiply R2 of theta and R3 of psi, then we have this final rotation, which is, you see, a little bit more complicated because now we have products. So we have cosine of theta times cosine of psi, cosine of theta sine of psi, minus sine of theta, and so on and so forth. We have the 9 entries. All right, so this concludes all the possible combinations of two elementary rotations that are independent. Of course, the next step would be to consider a composition of 3 independent elementary rotations. So we're just adding one extra rotation. So the first 2 steps are logically the same. We go from a reference frame A to A prime to A double prime, and finally we get to our reference frame B. And why are we considering a composition of 3 independent elementary rotations? Well, just because we're dealing with things in a 3-dimensional space. Our space is described using 3 dimensions. So we're really interested in the composition of 3 rotations. So the only thing that is different here is that the addition of a third rotation from the reference frame A double prime to the final reference frame B. And B is characterized by the same origin as of the first 3 reference frame and its set of versors B1, B2, and B3. So I'm using the same approach that I've used earlier. So now I'm still using a multiplication of 2 rotations, but now the first rotation that goes from A to A double prime is actually a composition of 2 elementary rotation, and that is what we saw in the previous step. So this first matrix R A double prime actually contains 2 rotations, the first and the second rotation. So what we are actually doing is adding by pre-multiplying another rotation from A double prime to B. So in the end, we have that the vector expressed in the A reference frame can be rotated or can be expressed in terms of B coordinates by using this rotation matrix from A to B. Now, what about all possible combinations for RBA? Well, we're going to have more cases, obviously, because now we're adding a third degree of freedom, if you wish. So now in this row, I have the 6 possible combinations for a composition of 2 elementary rotations that we saw earlier. So we're going to have R12, R13, R23, R32, R31, and R2R1. And I've excluded the 3 cases in which the 2 rotations were not independent. And now we're going to add a third rotation, which can be about the x-axis, the y-axis, and the z-axis of an angle that we're going to call with phi. So let's see all the possible combinations. And once again, we have to avoid rotations that are not independent. So for instance, in this case, over here, we would have R1, R1, and R2. Sorry, let me write it again. We would have R1 times R1 times R2. But you see that we have two consecutive rotations about the same axis, which will render the rotation not independent. So we cannot include this as a possible case. So I'm going to do that for other 5 instances. So we are left really with 12 possible choices. For example, R1, 2, R1, R2, R3, or R2, or 3, R1, you know, as long as we're not repeating the same rotation twice, one after the other. But we can have, for example, R1, R2, and R1. Again, that is possible because the two R1s are separated by an intermediate rotation about the y-axis. All right. So now I just want to point out that the 3 angles that, or at least notation-wise, usually they're called phi, theta, and psi. So they correspond to the 3 elementary independent rotations are known as Euler angles. So which rotations overall are we gonna choose? Which sequence of elementary rotation are usually used to go from one reference frame to another? Well, it depends on the application. The 2 most famous or 2 most common choices in order to get to our overall rotation matrix from reference frame A to B are the sequence 321 and 313. And again, 321 sequence, it means we first have a rotation about the z-axis, then the y-axis, and then the x-axis. So the multiplication of the rotation matrix is R1, R2, and R3 because we're going from right to left. Logically is R3, then R2, and then R1. And that's why it's called the 3-2-1 sequence. Okay. So just make sure that you're not that you're sure about this. And of course, for the 3-1-3, it doesn't really matter because well, it's a symmetric rotation. As a matter of fact, sometimes you're gonna if you find rotation matrices, they're like this: R1, R2, R1, and R2, or R3, R1, R3. These are called symmetric sequences because there's a symmetry. You have R2 and R2, R3 and R3. Instead, rotations or sequences, they are like these: R1, R2, and R3, or R2, R1, and R3 are non-symmetric sequences. All right, so let's consider first the 3-2-1 sequence. So if we write down the multiplication between R1 with respect to 5 times R2 with respect to theta and R3 of psi, then we get this matrix, then I'm not going to read out term by term because it's just going to take us too much time. But this is the result. And this kind of sequence, rotation sequence 3, 2, 1, is used extensively in aircraft dynamics. So you should get very familiar with this matrix because this is very used, especially when we want to transform from the local horizon, local vertical reference frame, so the LHLV reference frame that we saw last time, to the body reference frame. And I remind you that the local horizon, local vertical reference frame for the aircraft dynamics applications is considered inertial. And let me also remind you that there aren't any true inertial reference frames, but it really depends on the application that you're describing or that you're interested in. You can approximate a reference frame as inertial. So for aircraft dynamics, the LHLV reference frame is considered inertial, whereas the body reference frame is definitely not inertial because our aircraft continuously changes or it can change attitude and can accelerate in the translational perspective. So definitely the body reference frame is non-inertial. And for this particular transformation between the LHLV reference frame to the body reference frame, the Euler angles, well, they are usually, their symbols is kept the same, so it's psi, theta, and phi or phi, but their name are yaw angle, pitch angle, and roll angle. And their values for the yaw angle is between 0 and 360 degrees. The pitch goes from minus 90 to plus 90. And the roll angle, like the yaw angle, is between 0 and 360. And yaw, pitch, and roll are also known as the attitude parameters. Now, the same sequence 3, 2, 1 is also used to transform from the LHLV to the wind reference frame. So now the three angles, well, they are constructed the same way, but we're going from, well, the same LHLV, but to another reference frame. So obviously the three angles are going to be different from yaw, pitch, and roll. And in this case, if we construct this rotation matrix from the LHLV to the wind reference frame, the Euler angles are known with different names. And also the symbols used is different. So we have psi, which is the chi, which is the heading angle, and that is still goes from 0 through to 360. And then now the second angle is known as the flight path angle. We're going to see this in more details later on. So for now, just hang in there. We're going to give these angles a physical meaning. But nevertheless, for now, we have gamma, which is the flight path angle, and goes from minus 90 to 90 degrees. And finally, we have the velocity roll angle, which is phi of omega, and that can vary from 0 to 360. Now, the second most common sequence of rotations is the 313. And this 313 is extensively used in orbital mechanics, especially to go from the Earth center inertial, and so that's the inertial reference frame centered in the Earth and not rotating with the Earth, to a so-called perifocal reference frame, which is a reference frame that is fixed on the orbital plane of the spacecraft or the satellite. So we didn't describe this reference frame, and don't worry about it. Probably I'm going to mention it later on. But the only thing that I want to tell you here is that the rotation matrix between one reference frame to another is constructed by using a different sequence of rotations. So now we have R3, R1, and R3. So our matrix is different from earlier, and I want you to go and compare the two. Also here, I'm using different variable names. And in fact, in orbital mechanics, the three rotations, the three Euler angles are known as the, capital omega is the right ascension of the ascending node, or sometimes called the longitude of the ascending node. And its values vary from 0 through to 360. Then I is the orbital inclination, and that is a value between 0 and 180. And finally, we have a small omega, which is the argument of periapsis. So don't worry about it for now. I will probably give you some material about this later on. But again, now I'm interested, I want you to understand the concept of rotation between one reference frame to another. So don't worry about the physical meaning of these Euler angles. You're always welcome to go and do research on your own, but for now, just let's try to follow me on this. Okay, so the value of the argument of periapsis is still from 0 to 360. All right, let's take a look at an example now. And actually, let's take a look at the very example that uses the rotation matrix between the inertial LHLV to the body reference frame. So some of you might think, well, you've talked about rotations between two reference frames, but you always said that they have to share the same origin. And if you remember, last time we saw that the LHLV has an origin on the surface of the Earth, at a point on the surface of the Earth. But the body reference frame has its origin on the center of gravity of the body. So if we have an aircraft that is flying, well, obviously the center of gravity does not coincide with a fixed point on the Earth's surface. So how can we possibly apply a rotation between two reference frames that do not share the same origin? Well, the problem can be easily solved by always adding the distance, so the vector that is the distance between the two origins. So we can transpose one origin, one reference frame, so that its origin coincides with the reference frame, with the origin of the second reference frame. And in this case, we're gonna transpose, so we're gonna move the body reference frame to the origin of the local horizon, local vertical. So they're gonna share and have the same origin. Because once again, these rotations and these transformations between reference frames only make sense when we are considering frames that share the same origin. All right, so this is the assumption. And from now on, we're always gonna assume that whenever we're referring to transformation between two reference frames, they share the same origin, or if they don't, we transpose one on top to another. All right, so in this very example, we're given the three bursters of the body reference frame, but expressed in the LH-LV reference frame. So we have B1, B2, and B3 in the L coordinates. And so in this case, we have minus 0.542, 0.542, minus 0.643, and so on and so forth for the other. The question is, can we find the yaw, pitch, and roll angles associated with the 3-2-1 sequence of rotations that will actually give us these versors? Well, what we can do, so we are really interested in finding our objective is finding the rotation matrix from L to B. But we're given very precious information. So we're given the versors of B expressed in the L reference frame coordinates. And if we go back, so let's say we call, just to draw the parallel with what we saw, we had RBA, and we go back to these useful relationships. We find that RBA is given by the versors B1, B2, and B3 expressed in the other reference frame. So in this case, A is equal to L, placed as rows. So we can easily find that the rotation matrix is formed by the rows B1L, B2L, and B3L. Of course, the three have to be transposed. All right, but we're not done, because now we've just formed the rotation matrix, but we have to find the values of the angles of the three elementary rotations associated with the overall rotation matrix. So how are we going to do that? Well, we can take the general expression for a 3-2-1 sequence of rotation. So, and that is what we saw earlier. So we have this matrix, and we can find the angles by comparing the terms. So let's start with the easiest of them all, which is we have that minus sine of theta is equal to minus 0.643. So obviously, we have that theta is equal to our cosine of 0.643. And so that gives us two possible values. Remember, because when if you insert this number into your calculators, you're just gonna get 40 degrees, okay? But technically you have two values. In fact, both 40 and 180 minus 40, so 140, have the same sign. In this case, we're gonna exclude 140 simply because for this sequence of rotations, I told you that the pitch angle, so theta, it has to be between minus 90 and plus 90 degrees. So 140 is definitely not in that range. So we're looking at a pitch angle of 40 degrees. Now let's take a look at these green entries here. So we have that cosine of theta times cosine of psi is equal to minus 0.542. And then we also have cosine of theta times sine of psi, that is equal to 0.542. So let's take the ratio between these two equations. So we have that tangent of psi is equal to 0.542 over minus 0.542. And Well, and that is equal to 135 degrees. Now, there's a catch, and I'm gonna tell you later, excuse me, in a minute. So for now, just bear with me. It's equal to 135 degrees. Now, finally, we can take the other two entries, so the blue ones, and we find something similar. We can find now the angle phi. We have that the tangent of phi is equal to 0.262 over 0.720. So we have that phi is equal to 20 degrees. So it seems that we found all three Euler angles. So the yaw angle is equal to 135 degrees, the pitch angle is equal to 40 degrees, and the roll angle is equal to 20 degrees. Now, the thing is here, there's 135 degrees. Some people might not find the right value. And why is that? Because you have to pay attention to the sign of the numerator and the denominator. So I'm going to explain it with this notation. So every time you have an angle and you're finding an angle using the arctangent function, so you're going to have a numerator and you're going to have a denominator. Here I'm going to call the numerator with S because it kind of reminds of the sine, and C because of the cosine, and tangent is sine divided by cosine. But you can also have values of S and C that are greater than 1 or less than -1. So they don't necessarily have to represent the sine or the cosine of alpha. But nevertheless, let's say you have two values, S and C. You take the ratio and you apply the arctangent function in order to get the angle. Now, where is this angle? Well, it depends on the sign of S and C. If both S and C are positive, then we know we're going to have an angle that is in the first quadrant. So we have to expect a value of alpha that is between 0 and 90. If S is negative and C is positive, then we are in the fourth quadrant. So alpha has to be between 270 and 360, or between 0 and -90. If both S and C are negative, then alpha necessarily has to be between 180 and 270 degrees. And finally, if S is positive and cosine and the C is negative, I just slipped there, I said cosine, but C is negative, then alpha has to be between 90 and 180. So what did we have earlier? We had that 0.542 is positive, and the denominator is minus 0.542, so it's negative. And so we are in the second quadrant, and that's why we find 135. If you just input those values in your calculator, you're gonna get obviously arctangent of one number, in this case, S and C are the same in terms of magnitude. So technically you have arctangent of -1. But sorry, I think it gives you values between -90 and 90. Yeah, so if you input those values in your calculator and you just arctangent of -1, it will give you -45 degrees as the answer. So -45 degrees is equivalent to 315 degrees, which is 180 degrees away from the actual answer. So that's why you have to pay attention to the sign of the numerator and the denominator of the arctangent function. All right, this is all for today. and I'll see you virtually next time. Take care.